All right, so in this video, we're going to continue where we left off with the arch model. So in this, so for the generalized arch model of order Q, you get this. So you have your intercept and all the all the slopes or all the coefficients for the previous error terms, and it's linear and parameters. And then you can shorten the notation with the summation symbol over there. And in the arch model, we're remember the expected value. So then just in the arch model, the expected value of our error squared is going to be equal to the variance of our error term. It's going to be equal to sigma squared, or sigma squared t. And remember, and for this, something that makes it a little bit different than what we've done in the past. If we assume that that the error term is normally distributed, then we can pull out that standard deviation. So we'll say sigma squared multiplied by zt, where z is an IID, standard normal distribution. So a mean of 0 and a standard deviation of 1. So Z would be a zero mean white noise process with a variance and standard deviation equal to 1. Right. So then for this, if we apply it to or we test for it in our arch model, all of our alphas has to be equal to or greater than 0. And this is true for all alphas between 0 and Q. Because remember, standard deviation and variance are positive. It cannot be a negative number. It can be 0, but it cannot be negative. And if it was 0, then of course it's be constant. And this is to ensure that our variance is going to be positive. Needs to be positive. So now if we apply all of this, if we apply it to the actual arch model, so if we apply it to the actual arch model, if we say we want the expected value of our error term, squared, the expected value of our error term squared, given the previous values, we can get the expected value of a constant, just be the constant, plus, I'll do with the actual sum, get the sum of I to Q for all our alphas, all our other coefficients, multiplied by the expected value of our error term, t minus I squared. So we can factor out that coefficient. So assuming that this is stationary, and also assuming that the error term and the z, the epsilon and z are independent, assuming that they're independent, assuming that this is actually stationary, then we can solve for the long-term variance. So the long-term variance, remember that the expected value of epsilon squared is going to be the variance. This is going to be equal to the intercept plus the sum of our alphas, alpha I. Then the expected value of our error term again is going to be the variance. So we can move the variance over to the other side and factor it out, and we get that the variance is going to be equal to, the long-run variance is going to be equal to alpha 0 divided by 1 minus the sum of all other coefficients. So from 1 to Q. So this would be the long-term variance for an arch model. Then for the presence, so for the presence of arch does not affect the consistency of ordinary least squares. So whenever you do the whenever you do an autoregressive model, whenever you do an autoregressive model or a time series model and you use ordinary least squares, if there is a conditional heteroscedasticity, it does not affect the consistency of ordinary least squares. And then whenever you test for heteroscedasticity, remember for the arch model, I should erase this. For an arch Q model, the error term or the variance is going to be equal to, the variance of the error is going to be equal to our alpha 0 plus alpha 1 times 1 lag of the error term plus all the way to alpha q multiplied by q lags of the error term. And if you're going to test for this, the hypothesis test, the null hypothesis, so do an hypothesis test for conditional heteroscedasticity or autoregressive conditional heteroscedasticity. The null hypothesis would be that alphas from 1 to q, doesn't matter which one, of 1 to q are going to be equal to 0. Okay, do this in the wrong order. So the null hypothesis when testing for autoregressive conditional heteroscedasticity or for the arch model, you're assuming that the alphas for all the error terms, error squared terms, is going to be equal to 0. And this is for all I between 1 and q. It does not include the intercept, because if that is if that's non-zero, if it's positive and all the others are positive, that would mean that would be a constant variance, and the variance would just be equal to alpha 0. Remember that the equality always has to be in the null hypothesis. And for the alternative hypothesis, we're saying that alpha I is just not equal to 0. And again, this is for any of the coefficients that are in the error terms. And to test, you may use a t-test for a coefficient where, remember for a t-test, the t just be the expected value of that specific coefficient divided by the error term. That would be your t. This follows a t distribution. And this would be acceptable if you only have an arch model of order 1. But if you're doing if q is greater than 1, so 2 or more, then you should use a different statistic. So for this, you'd want to look at the number of observations minus the number of lags in the arch model, multiplied by the r squared, the regression. And this follows a chi-square distribution. But either way, it's a one-sided hypothesis test, and you're trying to determine if the alphas, if the coefficients are greater than 0. Let's do an example real quick before we move on. So let's do an example where we're looking at weekly stock returns. So let's say weekly stock returns are heteroscedastic, and we're using an arch model of order 1. Let's say we're looking at stock returns. So this is an example. We're looking at stock returns, and we get an arch order of 1. So Q is equal to 1. We get our error term is equal to 2.94. These are in percents. As plus 0.337 multiplied by the previous error term. And then the standard errors for these, 0.44. This one would do 0.036. The standard errors, so these are the standard errors. Let's say T. Let's say T which would be, of course, the number of observations. This is 688. Let's say our R squared for this model is 0.144. Remember, our null hypothesis is that our alpha 1 is equal to 0. The alternative is that alpha 1 is greater than 0. So first, let's do it in a t-test. So t is going to be equal to alpha 1, the estimate for alpha 1, so 0.337, divided by the standard error for alpha 1, which is 0.036. This is equal to 9.36, and this follows a t-distribution. So given a, so this is sufficiently high, given a 5% significance level, you could sufficiently reject the null hypothesis. So reject the null hypothesis. Let's do it again, but this time we'll do the other method. We'll using chi-square distribution. So our chi-square statistic is going to be the number of observations, 688, minus the number of lags, 2 = 1, multiplied by the R squared of this specific regression model. And this gives you 98.928, which is going to follow the chi-square distribution. And again, given a 5% significance level, this is sufficiently high enough, and we can reject the null hypothesis. Whenever you estimate the arch coefficients, to estimate an arch model, you're going to first create a regression model, and then you're going to estimate the coefficients based on the error term squared. Then you're just going to do an hypothesis test like we just did. So this is it for arch. The next video we'll do the GARCH model, which is a little bit more common in finance and risk management.